So this part is on the page 70, and I'm going to write this down for you guys. This is on page 70, and these are the real basic relations, which is quite important, and you must remember them here. So this is still in the same section for the moment. So these two relations are real basic, which I'm going to summarize them. A hat dagger applied to the eigenstate with the square root n plus 1, and then n plus 1 here. The n itself is the eigen state of the harmonic oscillator. If you have A itself without a dagger, and then this will be n minus 1. So just be sure there's a little asymmetry here. For the A dagger, it is square root n plus 1, but A itself is just n. But these two, just one is increase one is minus that one. So that is what we want. And the next thing that I want you to, this is on page, actually, what are the page numbers for you?
46.
46, okay. So this is electron. So my paper or electron 46. Page 46 like this. Okay. And the next, we're calculating expectation value. Could you guys go to page 71? And we're going to read together because the entire derivation is already presented. You see, if I want to calculate x, expectation value like x hat applied to n, and you notice that you can write in a way like A and A dagger. So essentially, A dagger, A without a dagger. And you have some coefficient in the front. Now, if you have an x squared, this is much harder when you do x squared. And then you also can do the same thing, which is the equation 3.10. So that's the equation. You also have some coefficient in the front. Then you have these crossing terms, A dagger squared, and a plus A dagger A dagger. So you notice that the permutation, they're not permutable. So you see, the first one is A dagger in the front, and the second is A dagger in the behind. So these two are not permutable. In other words, if I multiply by x by itself, you will have 4 terms total. So then you will have this term plus the final term will be A hat like this. So total we have 4 terms. Can you imagine just this one times itself by 4 terms? But watch carefully. You see, A dagger A dagger, they are not the same. This is a very different if you just remember geometric expansion like this. You'll get x squared plus 2xy plus y squared. But here, y squared is y squared, x squared is x squared, no problem. But this guy is not twice this amount. Can I get acknowledgement from everybody of you? So just make sure this is the difference. You know, you have to do it in the operator way, not geometrically. So this is the difference. So once you know what this applied on that, and folks, let's turn to the next page, please. So then you can calculate for the equation 3.3.11. So that's the equation which we can calculate. So we can calculate expectation value of x squared. In other words, you will get something like this. X squared and like this. You can calculate this immediately. And when you do that, you will end up with this equation. 2n plus 1 divided by 2m omega h bar. And this is what you will get. So this is what you will get. The results for the square term. Now the x term itself is 0. So in other words, x term itself is 0. If you calculate, because then you can imagine this is going to be 0. N x hat n, and this equals 0. So there is no equilibrium position equals 0. So this is the absolute R0 case. So then you can see the uncertainty for the harmonic oscillator in the position is just square root 2n plus 1 2m omega h bar. So this is the uncertainty involved for the position operator. You could also calculate the uncertainty for the momentum operator, and this is the bottom equation there. You will end up with n plus 1/2 h bar omega. Now, if you multiply by these two together, multiply them up, essentially this equation times that equation, and this is a px, and this equals 2n n plus 1/2 h bar. So this is the entire calculation. You see, you don't need a lot of mathematics to do the calculation, and this is a generic equation. Now let's look at the uncertainty principle. Uncertainty principle says from the uncertainty principle, it must be larger or equal to half h bar. So it must equal this amount. Did you see if for this equation, if n equals 0, for n equals 0, and this delta x, delta px just equals 1/2. The 1/2 h bar. And in other words, the lowest possible uncertainty you will get, that lowest, you cannot be better than this. Lowest uncertainty is precisely at the uncertainty principle's limits. Is that neat? And this is the minimum. You cannot be better than this. You could be larger. When n becomes larger, uncertainty becomes larger, 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 larger like this. But when n becomes smaller, uncertainty will be smaller, but never being able to break down this particular barrier. So that's why the uncertainty principle always survives, regardless how tricky you want to make experiment with, and you never win. So quantum mechanics always win. And a lot of people try to break this down. Well, it's not possible. Even the harmonic oscillator cannot break. So there is no other way you can break the this particular equation. So that's impossible. Okay, so this is what I left over, and I leave some homework for you guys to work on some of the things because the details are represented like that. Okay, any questions before I close this particular section? We're going to start with new section now. New section turns out relatively straightforward. Okay. Any questions on this part? So essentially, when you work on the homework a little bit further, and you'll get a better understanding of this. Now, our job today is actually relatively easier for us. This is our section 4. And this is called a time evolution. In this section, we will focus on the Schrodinger's picture. Schrodinger's picture is simpler for us to understand the entire physics. So that's why we started with this one earlier. And the Schrodinger picture, essentially, we will evolve with the time. So this evolve with the wave function. Evolve with the wave functions with time. So this just tells you that we will evolve the wave function, and that is what we will do in this case. So that's a key message in the sense that what actually you're going to see them. So the key message is that we're going to evolve the wave function with the time. And so this is the one which and you will find a little boring. But please sort of hold on to this because it's a little boring in the sense that I will show you the same equation repeatedly again and again, but you probably will like it also. Let's first look at the pure state. So this is a pure state. Pure state's evolution is extremely interesting, also much, much simpler. So in the beginning, we have a pure state. And at the time t equals 0, so I just put the phi sub n as 0. So that's the pure state. Now, t not equals 0. And now you should be able to tell me what you will get. What you get, Cody? What you will get? At t not equals 0, what will we get? You remember something? Alex, can you help? What we will get? If this is the pure state. Let's stop with the number.
It would be 5 times e to the
Keep on going. E to the
I bar t over.
Yeah, pretty close. I know what you're going to say.
Negative I omega t over h.
Yeah, well, something similar. Aisha, can you add a little more? Could you guys write this down in your notebook? Let me take a look at this. Yeah, let me take a look at this. Write this down in your notebook. I just want to read it instead of, yeah, just write it down. Finished? Yes. I want you to take a look. Write it down in your notebook. I just want to enjoy them because it's quite important. Let me take a look. Good job. Yeah, you write it there. You write it out somewhere. Write it out somewhere. Okay, I see. Now, write that down. I read all of yours. Keep on writing. Okay, all right. All right. Well, I thought originally it's going to be boring. It's not boring at all. Not everybody got it. We got a 50% student got it correct. The other 50% not. Watch carefully. E to the negative I, E sub n, h bar. Did you see that? Could you guys write this down for those of you who did not? You remember something, but that is what you need to remember. And then phi and 0, like this. So this is the time pure state. And now for the mixed state. For the mixed state, this is just superposition. For the mixed state, and then all you need to do, I'm not going to do the phi now, I'm going to do the psi, because that's a mixed state. Mixed state, so we'll be t is equal 0. Suppose you have some kind of a combination of the rest of these other states like this. So that's that. And then the time-dependent state is going to be real simple. And you just copy everything there, and then change this one to the C and e to the negative e and t, and then you have phi sub n. This. And that's all you need. So there's no other magic things involved. Yes, I can read it very easily. So good. So this is essentially what I want to show you for a mixed state. So pure state you do like this, mixed state you do like that. So that is one we did. And one last thing, which we're going to show you, if we want to calculate expectation values. For instance, we have an operator. Let's call it O hat. Toby, you got a question for me, did you? You had a question before this? No. When I was asking this. Oh, you didn't know my question. Okay, that's fine. And let's do that. For instance, if we have expectation value, and then we will do something like this. And I'm not going to rewrite the whole thing. This is basically the same ones. But I do want to write down the first time, of course. This will equals nm. So the left-hand side, I use n character, cn dagger, also start forget not dagger, and phi in this direction. And then just keep in mind, I use the n index symbolize the bra part. this broad part, I use N. And then I use the kid part, use the index M to representing it. So this will be operator. And then this kid part starts, so I can move this Cn to the front. Cm to the front. Folks, could you inject one particular Cm here? And then I will have the, instead of N, I will have M, this part. And this M is the kid part. This is the kate. This is the bra. So in other words, when I have two of these, and bra will be on the left and kate on the right hand side. Then all I need to take out this particular phase factor. So I'll put the phase factor on the end. And this will be, originally, did you see I have a negative sign here? But once I take this conjugation, this is become positive. So therefore, you're going to see me to write a positive. And the end part will be negative TH bar like this. So that is the entire calculation in the following way. Now when we do the time evolution, we get everything. So that's time dependence. And so we're going to look at example, page 74 to 75. And Aisha, I will tell you which one is. We're going to read the example in the textbook. This is example 3. Example 3. And I'm not sure what the page number. You will see has about a certain principle in time domain, a harmonic oscillator initially in a mixed state, example 3. And just below the equation, the equation numbers. So this is the one that I'm talking about. You find it? Okay, that's 47. Page 47, this problem. This example. Okay, good. Folks, I give you 5 minutes to read this example. I will tell you there is a correction in a minute. So, but just keep on reading this question. If you have any question, just let me know. finished? Any questions? No, not the same question. Okay, good. Take your time if you have questions. Just let me know later. I'll be able to address them. Question? Yes. So this plus 1 is coming from the fact that I change always a plus 1 up a diagonal a. You know what I did was, it's a great question. I'm going to write over here. So, and I have a dagger. So I will have term like this. Now, you may wonder why I always like this instead of like that, right? That's the question you would have.
Yeah.
So the main reason is this. If a dagger a upon n, this is equals n, like this. So I can immediately know the results. But if I have a dagger, this is not equals n. So in other words, I cannot simplify the expression immediately. That's the only difference.
Because that would be the last class where we have to look into the back.
Exactly, exactly. So then what I did was, I like this because I can apply any eigenstate equals n times n eigenstate. This you cannot do it. So then I convert this guy, use this relation, equals 1, you see a dagger a. Sorry, a little busy. Let me erase those ones here. I need it here. So in other words, let me write over here. So a hat minus a dagger a equals 1. And then any of these terms is going to equals. I'm going to move this term to the right hand side. I get a dagger a 1. The 1 in the book is just come from this one here. And then this term and this term, that's where you see the twice of this a dagger a. So that makes sense to you?
Yeah.
Okay, so anybody else has questions on this? Anybody else has questions? Now I have a question for you guys. If you don't have a question for me, I have a question for you. Yeah, oh, you got a question for me?
Yeah.
Go ahead.
So whenever it goes from finding the position expectation value, when it says using the relations of a dagger in and just a in to get that the non-diagonal terms stay, or the non-diagonal terms equals 0, but the diagonal terms stay.
Off diagonals will be, yeah, exactly, yeah.
Why, I'm confused on why the diagonal terms go away.
Why the diagonal term goes away? This is a really, really great question. And Toby, I'm going to show you here. How about that? Okay. And why the off diagonal remains, but the diagonal term, it's gone. What's the other reason? And I'm going to explain this to you. Let's just pick up this as an example, just a dagger like this. Maybe I'll write over here would be better. Well, let me write over here would be better. So I'm going to write this over here. So a dagger n, we know this equals n plus 1 n plus 1. Okay. So that's what we already mentioned a couple of times. Suppose I'm interested in the diagonal. Suppose I'm interested in diagonal, so I would have, this is diagonal terms for this guys, right? If I put the diagonal on the left vector n, then this will be on the left factor n. Look at this one here. This is 0. Because eigenstate, different eigenstates always orthogonal to each other. Different eigenstates are always orthogonal to each other. In other words, this one here, this this is equal 0 because different eigenstates are orthogonal. Because different eigenstates are orthogonal to each other. If you don't like this expression, what this expression does is just like this. So this is what this is doing. That's just a diagonal term. Off-diagonal term is 0. That's why. So whenever you have off-diagonal terms here 0, the diagonal terms here will be 0. Because the orthogonality between the eigenstates. I'm not sure whether in other words, just make sure we are talking two different things right now. Two different things. This is eigenstate orthogonal to each other. This is the elements of the operator self. Diagonal terms of operator expectation of element self. Off diagonal term remains, the diagonal term is gone. So this is the metric elements. Metric elements of a set. While this is the wave function themselves. So they are different. I'm not sure whether I explained this to you clearly.
I kind of get it.
Yeah, let me word it slightly differently. Let me word it slightly differently. And I want to show you why this must be, diagonal term will be 0. And I'm not going to use the mathematical. I'm just use a physical picture to show you. How about that? Let me show you. Suppose we have one level. This is the one level n. That's eigenstate which we have. We know this A dagger, when you use it, it jumps, right? It jumps. So now it's going to jump from one level to another level. Because when you have A dagger path, it will jump to another level. Since you jump to that newer level, this newer level has no overlap with your previous level whatsoever. Because you jumped. If you don't jump, well, you will have values. Because you jumped. So that's why we 0 value. In the meantime, you notice that if I have A dagger A like this, if you have two operators, you will have non-zero values. The y you see here. Suppose you jumps over here, but this operator jumps back. Did you see that? So therefore, Aisha, that's the main reason we put it in this way. Essentially, we just go up and boom, going down. So then diagonal term will remains. Diagonal term will remains. So diagonal term will remains when you may have like this. So if you have a single operator, if you pair them together, the diagonal term always remains. But if you have odd operator like this, not odd operator. Now, if you have not appearing pairs, if you do not appear in pairs, look like this. So you see, they do not appear in pairs. A and A dagger does not appear in pairs. Now you see, if you do this, you will jump twice like this. So then this off-diagonal term will be 0 again, because diagonal term will be 0 because you jump boom twice. But each time when you have A dagger paired to each other, the diagonal term will remain. Off-diagonal term run because you go up, boom, going down. So that diagonal term remains. And it looks better this time. Essentially, when you have a ladder operator, it just means that I jump one level. If you did not come back, sorry, you only have a off-diagonal term remains. But if you come back, you have a diagonal terms. And we will practice a little further. Don't worry for the moment. That's the purpose of this practice. Sounds good? Sounds good? Any other questions? This is a really, really great question. So similarly, if you have these two A like this, and then it will be this will be the diagonal term will be 0 without anything. Off diagonal term could remains. For instance, if you have let's say, just to be concrete, let's say if you start level 3, apply the 1s, it jumps to 2, right? This is the annihilation. apply another one's jump to 1. Make sense? So therefore, if you have the state on this side is a 1, this will be non-zero. So 3 minus 1, get a 2. Another one, 2 minus 1, get a 1. So if the left-hand side is a 1, then this is a non-zero. On the other hand, if the left hand is 2, this will be 0. So this is essentially just like each time when you apply the operator A, you jump to one level. Then ask you what the bra is. If your bra is the already one level, yes, that will be non-zero. And I do not just skip this. I want to show you entire table for this. Let me show you entire table. In other words, so you have a much better idea how this works. I'm going to show you here. Let me write over there. Instead of trying to erase this, let me go over here. And this part is really, really crucial. I'm going to show you entire table. I show you entire table. Everybody just write. I did not write this in my notebook, but I definitely write this table will be much better for you to understand the entire physics here. So my row here refers to quantum number n. Okay, row means quantum number n. The column here refers to quantum number n. Okay, sounds good. So I have a quantum number n starts here. 1, 2, 3. So that's n quantum number. And this is essentially, this n, I want to be precisely, this n means this is n, and I have a like this, n over here. So this n is this n, this n, and this n. Make sense? So that is what we have. Suppose you start with the n, which means this guy is n, 0. Now n applied to any 0 state, so this is the first element, is going to be 0. Again, a applied to that, any state. This is because a 0 always equals 0. So this is the 0 state like this, no problem. Now let's apply it to 1 here. Apply it to 1. So this time we're going to apply it onto 1. So in other words, in my here will be applying to 1. Now, applied to 1, this gave me 0 state, not 0 itself, gave me 0 states. If my m equals 0, and this will give me a value, 1. Let's look like that. Does it make sense to you? In other words, if this n applied onto that, I just want to show you extremely detailed. A, gave n. N minus 1, n minus 1, like this. If n equals 0, this entire term equals 0. But if n equals 1, if n equals 1 here, and this will be 0. If n equals 2, this will be square root 1, and this will be n. This will be equals 1, like this. If n equals 3, this square root 2, like this. But can you see here, if I apply to this, so whenever 1, 2, 3, this will be 0, 1, 2. Make sense? So these all off-diagonal term will remain. Is that correct? And so that's why, if this equals 1 here, so I get a coefficient 1. If this equals 2, I will get coefficient 2 here. So this will be 1, 2, like this. So this is a 2, element 2. Here will be square root 2, like this. So that will be square root 2, like that. And then you can see systematically. So all the diagonal terms, all the diagonal terms will be all zeros. This is all zeros. Everywhere here will be 0, 0, 0, 0, 0. All these diagonal terms will be all zeros. And then off diagonal term will be square root 2. The next one will be square root 3 3, like this. Toby, you see here, if the next one is square root of 3, in other words, this one level jumps over here, will be square root of 3 like this. And that's the one metric elements. I hope not confuse you more.
I'm getting lost on the notation.
Which
So,
notation?
If n equals 2, then you get the square root of 1, 1, which turns into the 1, 1.
Uh-huh. N equals 2, and n equals 3.
Yeah, so I understand how you're getting that, but where's the m come into play?
Oh yeah, this is for the moment. I was thinking you're good so far on this part, right?
Yeah, I understand.
Now, all right, that's perfect. That's perfect. That is great. Now let's see where the m comes out. That's exactly what we want. Now let's put m comes out. M equals 0. Suppose m equals 0. Now this time let's do the m. Okay, so m equals 0. If m equals 0, then let's put m over here. This is the m. So this is the m here. So this time we put the m here. So in other words, when a applied to 2, you get a 1 like this. So then if you have a bra comes out, this word becomes like this. Make sense? If the bra comes out of the m times with the k, well, are we good from here to there? It's that if you do not put m, this was the relation you already understand. Now, if I have a bra part comes out, Toby, it will be m vertical line 1. It's good. Now, this term only be non-zero if m equals 1, because of orthogonality. So this term only will be non-zero if m equals 1. So that's the key. I'm not sure whether the rest of the students got an understanding. You know, if this expression non-zero, the only case it's true is m equals 1. If m equals 2, the orthogonalities gave you 0. So you know what, this term is the only way that you can survive is m equals 1. There's no other way. There's no other way. That's m equals 1 is the only choice. Are we good? You know, whenever this term comes out, non-zero, only way that this comes out m equals 1. In other words, you only have elements like a 1, 2. Here's a 1 and 2. You know, here's a 1 and 2. So here, this should move over here. 1 and 2 like this. So this is the only one we will show up. 1, 2, 2, 3. I need to move this one column further. So here's a 1, 2, 2, 3. Let's put a cross, will be non-zero here. And 3, 4, maybe 1 further. So essentially that's orthogonal elements comes out. So here's a 1, 2, 2, 3, 3, 4, like these comes out. I'm not sure whether I understand, explain. At least it's better than you started with, right? So essentially just to show you these are the off-diagonal elements showed up. So these are the off-diagonal elements. Any other questions, students? And this is how we calculate these equations in this way. Let me summarize it such a way that you will understand a little bit better. How do we do the calculation in this way? Let me summarize it. Here's a summary. When we calculate these the wave functions, we always have these operators. Let's just put, to be more precise, let's say A, dagger A, M, like this. Suppose these operators, one is A dagger, one is A. And then this must equal some coefficients, and then this time we will have a delta N M. This delta LM is called a chronicle delta. If n equals n, and this will equals 1. If n not equals n, this is going to be 0. If both A dagger A appear at the same time. On the other hand, if we have two daggers like this, if we have two daggers like this, and we also, of course, we have some coefficient in the front, then this n, not n anymore, it has to be equals n plus 2. So if the only way that this survives must be n equals n plus 2 for this plus sign. If you have a minus sign, which is with that dagger, without a dagger, now watch carefully, you will see n minus 2, like that comes out. It is these minus 2 plus 2 that give you off-diagonal terms comes out. Diagonal terms will show up something like this. You have some coefficient in the front. And for this reason, you see, I always use this one much simpler. If you use a dagger, then you will run up the situation. You do not equal to immediately use this. So there's a waiting time when you see a dagger, you're going to convert to a dagger a, like this. So that's doing the calculation. If I have similar things on Wednesday's quiz, make sure you remember this. Okay, so the a dagger a is good. A dagger, you need to convert that to a dagger a. I'm not sure whether you understand what I'm saying here. Essentially, whenever you see this, you can convert to this. Okay? Make sense? Then when you apply the eigenstate, we'll pump out the n in immediately without any worry. But if you do this, you need to convert them. But if you already got this equation, you are perfectly fine. All right, sounds good. Any other questions before we close this? Sounds good. Okay, very good. And on Wednesday, we will have our quiz, another quiz, and this is going to cover for this chapter, and it also consists some question part, and also we have a bonus for the exams part. So I will have separate problems for the bonus, so such a way you can promote your grades a little better. Do you like a bonus points? You like it? You like it? You like it? Okay, perfect. That's what we'll do it. Make sure you prepare well, and so we will see you guys on Wednesday.